is to try to describe this. Let's imagine that we have a string. We studied it. We know Mersenn's law, velocity, wave function, velocity for the string is not like that, but it is similar. Which kind of force is deciding this velocity? Well, it's the tension. Trying to put back the system. Since you have done your beautiful homework and you have been going through the past slides, you should remember what is the vertical restoring force in a string.
Tension times cosine of that.
Good. Do you remember how we have been writing it?
Yeah. Tension times tan of theta. Or
Right.
derivative.
Or the derivative of y respect to x. It was the derivative, not the displacement. Force is related to derivatives. Displacement is related to itself. Okay, now, so what we're going to study is this junction between two different strings. We will imagine to have the same tension, but different densities. Different density means different velocities. We are going to generalize this concept speaking about a contrast of impedance. Impedance is a word that is used in many cases. In seismology, for example, in geophysics, applied geophysics, in circuits, and in strings, and also in acoustics. Can we generalize the concept of impedance? Well, let's start from a string. It's a mechanical impedance. We can define impedance speaking about the ratio between the force, that is the actor, and the result, that is velocity. It's a way to define it. It's a definition. Let's try to write it. Okay. Now we go back to the string, and we do remember that the force, the acting force, is related to this. But the tangent, if the angle is small, can be written in terms of the derivative. And if you compute the derivative using a general expression like this, you're going to put down here a k. A k is omega over v for any wave. Okay, what about the transverse velocity? Now it's time to take the time derivative. Omega is coming down. If you compute the ratio, what you're going to have here, this ratio, it will become this, it will become this. Now, I played a trick here. I've been calling linear density in terms of density. Why? Because this is the general definition of mechanical impedance for every system. If you want to see another example that is more common, we can discover what is called acoustic impedance. And if you compute it, it is going to be defined pressure, that is the force that is acting to create a sound wave, and the result, the flux. If you take that ratio, you're going to obtain exactly the same amount. And what is funny is that if you're going, when we are going to speak about seismic velocities, so if you take a layer of the Earth over another one, its impedance will be characterized by the same quantity. So the message to take home now is to, okay, we have a mechanical system. It has its inertial force characteristics, and we can characterize its impedance by that product. Now, let's imagine to join two strings with different densities. They will have different velocities. They will have a different impedance. And please begin to think also about the extreme cases. Let's imagine that we have a string with a fixed end. So we are arriving, oh, cannot do anything here. That system has an infinite impedance. Okay? In the other extreme case, let's imagine that we have a free end. So we have a string, a ring, a stick, and it can oscillate. It can oscillate without friction. That's a free boundary. So we arrive here, and that part has zero impedance. So we have these extreme cases. Good. Given this definition, it's time for algebra. Now, this set of slides is coming from the textbook of Steiner and West session, that is Introduction to Seismology. Is one of the books that I've been suggesting to you. It's written in the syllabus, hoping that the system will go up again. You have many copies in the library. You have many ways to find a PDF copy of the book. Some legal ways and some not legal ways. And especially when we are going to speak about seismology, it will be a sort of a textbook with many exercises inside. Let me tell you that part of your second and third homework will be based on those exercises. Okay? It's a very simple book, it's a very clean book. And Senwa session also provided the slides available. So I'm using that. So this slide here is coming from a textbook about seismology. But it's not seismology. It's a welded contact between two strings with different impedance. Now, we have some energy.
What's the name of the book?
Look, if you're able to. Okay. That's the book. Okay? If you go back to, let's see, maybe the system is on? No. In the syllabus that was uploaded there, there are a set of references. One is in bold. It's this one. It's the most important one. Okay? So, again, if you Google Steiner West session, you will get it immediately. Let's forget about this for 1 second, and now let's study the system here. So what do we have here? Well, we have an endless on the left string, and it is connected to another one. Part of the energy, so we have been shaking it, there is an impulse, a wave function that is traveling, going to the boundary. Our guess is part of the energy will be reflected, part of it will be transmitted. How much? How? Well, let's apply the boundary conditions. Okay, that's our guess. We have the ingredients. We are going to cook with a recipe. We will have the dishes. So this will be reflected, look at the plus here, and this will be transmitted, look at the minus here. Please give a look that, please notice that omega is the same, but k is not. Remember that k, omega, and velocity are related. So if we change velocity because we have changed the density, k will be different, and wavelength will be different. That's why here the wavelength is not the same as here. Now this is a specific case. Give a look. This line representing the second part of the string is, okay, thicker. What does it mean? That its linear density is higher. What does it mean? That its velocity will be shorter. What does it mean? That wavelength will be shorter given the same frequency. That's why this is smaller than this. But it's a guess. We did nothing up to now. What we have now to do is to apply the boundary condition, looking for what? For B and C. These are the unknowns. Okay. What about the boundary condition? They will be giving us two equations. The first one will come out from what we call displacement continuity. the string cannot break. So the displacement at the junction has to be equal on the two sides. It's continuity. The second boundary condition, coupled with the first, we are going to give what we call a welded contact, is saying, okay, look, the force on this side and the force on this side cannot be different. We cannot create corners there. Otherwise, the system will have an infinite acceleration in a single point. So also force has to be continuous there. Which force? The vertical one. If you want, we are going to apply the continuity of displacements and forces. Let's give a look to the first one, that is a simple one. What we have to say is that the left side and the right side at this position here, they have to be always the same at any time. We are so smart that we are saying that the junction is in x equals 0, so we can throw away the dependence about space. So actually, what this is saying is this. And since this factor is common, that's the first equation. Second one is a little bit more tricky, but we have to say, okay, look, left, right, let's compute the force. This tau is our T. Okay, it's the same, it's the tension. But now derivatives are going to work here, respect to x. So actually we have to take down k1 and k2 and take care about the signs. Minus, minus, plus. Okay, k1 over k2, but that's omega over velocity. And so you can rewrite this in this way. Look now, there is the product between density and velocity. That's impedance. Okay, now we have two equations in two unknowns. Let's couple them and let's solve them. What we can find is the ratio between B and A and C and A. We can call it reflection and translation coefficients. Now please give a look. Their amplitude is proportional to the impedance contrast. Let's imagine that the two strings are equal. If they are equal, what will happen? Well, this is going to be 0 and this is going to be 1. All the energy is passing. But if they are different, part of the energy will be reflected, part of it will be transmitted. And it can be shown, also if we will not go into the algebraic details, that energies are conserved. Now please remember, energy. In this case we have to take care about two energies, potential and kinetic, as usual. We have no damping here. If we're going to compute the flux of energy, it will be constant. In other words, energy is proportional mainly to the square of the amplitude, both kinetic and potential. And if you're going to compute the flux of energy that is passing, transmitted, reflected, whatever, it's going to be conserved. What are the ingredients? Well, the square of incoming wave. That's the energy that is entering. Then it's going to be partly reflected, partly transmitted, but the sum of the squares, in some words, in poor words, it will be constant. Okay? Now, can you imagine two extreme cases here? Well, we could. Because you can imagine that one end is fixed. Now the second string is fixed. Well, in that case, that impedance is infinite. We cannot move it. If it is infinite, well, and if you take this limit here, what you're going to get is -1. What does it mean? All the energy is reflected with a phase reversal. -1. Let's imagine that that string is nothing and you have a free boundary condition. That's zero impedance. And if you take the limit, it's going to be 1. All the energy is reflected without phase conversion. So we have shown what we have imagined in these two examples here, 1 and 2. So we generalize the junction, and we can take care about impedance contrasts and also the extreme ones. Now, given this relatively boring part, now we can imagine, so you see that's the situation. According to the values of the densities, part of the energy will be reflected and transmitted. Taking care about the energy conservation, and remember wavelengths. Wavelengths, lambda, it's embedded here. By definition, it's a wave number, okay? But K is also omega over V. And lambda is nothing else. That's true for every wave system. Or you can write it over frequency. This is period, sorry, not tension. Of course, it's period. What does it mean? What does it mean? That if velocity is lower, wavelength is shorter. That's why in this picture here, you see on the right, wavelength is a little bit shorter. Okay, and as I was telling you, if you do the computation, but we will not enter into the details, and if you compute the kinetic energy in one wavelength, and you compute it, that's velocity squared, okay, you get this. No news here, because we have the square of the amplitude. Oh, please do also remember what we discussed in the last lecture: energy, power, intensity, decibel in some cases, okay? And the square of the amplitude is always there. Okay, what about potential energy? It's a little bit more tricky because we have to compute what is the force and the work that we are doing trying to wiggle the string against the tension. That's why I don't want to enter into the details, but if you do the computations over one wavelength, what you get is exactly the same. Now, given this definition, if you look for energy conservation at the junction, it works. Because you can demonstrate that the energy flux incoming is equal to the energy flux outgoing. Okay? Good. So now we can understand physically what is the birth of the standing wave. Because now we can imagine a situation in which energy is arriving, bouncing back, and they interfere with the one that was arriving here. We did this at the end of the last lecture. Wait a second, let's wait for this. Progressive, interference with regressive, standing. Okay, please tell me.
In the previous picture, the graph part.
Pardon?
The picture, the plot.
The picture? Which one? This one?
Yeah. Can you say there is a phase reversal here in the second picture? Because it is free?
No. If it is free, there is no phase reversal.
Yes.
If it is fixed, all the energy is coming back and it is phase reversed. Now, in this case here, the reflect is reversed, but why?
It is fixed, I think.
No, it's not fixed. That's welded contact. Now, this is not fixed. Wait a second. The fixed end case is an extreme where this point here is 0. You cannot move it, okay?
Yes.
But this is thicker, okay? This is the case, light, thick, okay? Are you following me? Now, if it is thicker, its impedance is larger. And if it is larger, reflection will have a minus. Now, if you take the other case in which you have thick and light, you will have reflection and reversal. So, amplitudes and phases here are related to this. It's not fixed. Fixed is an extreme case where this bold line here is a point. You cannot move it. There, you can move it. In one of the slides, I have an animation of this, but not in this one. Look, that's the general case. Here, we consider two extreme cases. Fixed. This is so thick that it's a fixed point, a pin, okay? That boundary condition means that the displacement there has to be always zero. The other extreme case is that this thick line is becoming nothing, and there you have maximum amplitude, but force is zero. It's called free end. So fixed, free, welded contact. That's the general. You can imagine two extreme cases here. This is infinite, this is zero. So this picture refers to the general case. Okay? Good. Now, let's move to the discussion of standing waves. And this is a sort of reprise of what we did at the end of the story on Friday. Now we can imagine, using the superposition principle, we have a set of waves that are arriving on one side. Another set, thanks to a border, for example, to a fixed end or to a free end, is coming back. What's going to happen? Okay, we can do the summation. We can use some beautiful trigonometric expressions that you will learn using your memory. I'm too old to do that. And we can rewrite that sum in this way. Now, space and time that in a progressive wave are connected by velocity, now they are separated. In time, what's going to happen is that some points will vibrate at their maximum, and it is dependent upon this. Some points will be always zero. Antinodes, nodes. But what is important is that the total flux, lateral flux of energy, is zero. Because part of it is going this direction, part of it is going this direction, it's zero. Energy is localized. It's not progressive. Okay? So in my opinion, the best way to understand this is this animation that I've shown to you, but I prepared another one looking at the water fan. So look at this. Progressive, reflection, beginning of interference, standing. Now it's going to loop, so it will be a mess. That's my problem. But now there is no progression. It's standing. That's the looping. Forget. This is not physical. It's just a movie effect. Okay. Now I prepared here. I hope that it is still there. This. Let's say that your homework for Wednesday, you're going to receive on Wed some homework, official ones. So be prepared. That will be very simple. Is to go back to this and study it. Now, what is this? Incident wave. Okay? It's arriving here. I've chosen a fixed end. So when energy is arriving there, the boundary condition is saying that point has to be fixed. All the energy will be reflected. Okay, some reflection now is going to start. The blue one is the reflected. Now it's going to be overposed to the other one. I can, look, oops, let's forget about the reflected. Now this is what's going to be formed. And if you wait some time, now, thanks to the interference, now energy is localized. Well, it depends where you're shaking your string and the frequency, of course. Okay? Now, what about a free end? What do you think is going to happen?
Complete energy being reflected.
But the end of the story? Oh, my God. We would wait forever. I cannot accelerate it, I can only decelerate it. So it's the same, the incident is the same. It will arrive there, it will be reflected, but without phase inversion. And the end will be free now. What does it mean? That force there will be forever zero. And you see that that point now is going to oscillate with maximum amplitude, and here it's never going to create a derivative, because remember that the force is proportional to the derivative, dy over dx. Okay, now, if you see there, the pattern will be very similar to the previous one, but it's shifted. Essentially because here, now let's forget about the incident and the reflected, it's shifted in space. Because now here you will need a maximum. It's a boundary condition, not a zero. Okay? What we have to do now, but we will go relatively, let's remember that this is the simplest case of boundary condition. We have a 1D system, one dimension, so we have one point. Now what to do next? Okay. We should start to describe this wave function here, that is a wave function that is no more related to progression of energy in space and time. It's not moving. Its motion, it's localized in some antinodes, and it is zero in some nodes. Where do they happen? Well, it depends by the spatial function. Where the sign will have zeros, it will be forever zero. Where it will be maximum, it will be always the maximum. And the points will oscillate with different amplitudes according to this one with the same frequency. Okay? So, actually, every system, every point of a system is oscillating with a given phase with the same frequency. If you do remember the definition of a normal mode of a system that we have, considering the trivial case of a harmonic oscillator, just one point, but with 2, with 3, with 4, we characterize, we called these motions the normal modes of a system. Okay, what's next? Antinodes. They occur where the sign is a maximum, of course. So they have a very definite spatial cadence, okay? They're periodic. And they are out of phase by lambda over 4 with nodes. Okay. So it's very clear motion. What is important, it's no more progressive, and space and time are separated. Okay, what's next? This. High school physics. Now, this is the simplest and the most typical example of a world with boundary conditions at the end, at the two ends of the world. What should we do? To look for solutions. Well, actually, we already done that. But let's imagine this was your last homework, but I'm sure that you have not completed it. I've asked you to consider the wave equation and to separate variables. Oh, God. You see, that's the funny part of not assigning official homeworks. But let's try to do it now. Now we have a string with a given length. It's given. It could be 1 centimeter or 10 meters, but it's given. Okay? Now we have a wave equation. Right? And we solved it. D'Alembert solved it. F of x plus minus dt. Good. From the big pot, we consider these ones. Why? Because they are nice and useful, as we will see in the first tutorial about Fourier. Good. Now let's start from scratch. We have a wave equation, and now we have a boundary condition. For every t. These are two boundary conditions. Your homework was supposed to think about this by separation of variables. It would be today's homework. Come on, guys, let's separate variables. Let's see what happens. It takes 2 minutes. But what you have to do is to consider this separation of variables, plug them here, look for two differential equations. Oh, it's easy. Second derivative, coupled by v. You will get two differential equations that are exactly the same to the harmonic oscillator. One will be in x, the other will be in t. What you're going to get is that the x will be a combination of two independent solutions. Which ones? Cosine and sine. Time will be a combination of two independent solutions. Which one? Cosine and sine. Now, what about this? Here, the string has to be fixed. What about the cosines? Can a cosine be 0 in 0? No. The sine is 0 in 0. So the boundary condition immediately decides that the cosine is not good, and we have to take the sine. What about the second one? This has to be always 0 in L. What does it mean? That KL is quantized. What does it mean? Oh, K is 2 pi over lambda. Oh. And now we have found the wavelengths of normal modes. The first, because actually its wavelength is 2L, n equal 1, n equal 2, n equal 3, n equal 4, 5, 6, how many? Infinite. Infinite numbers, because n is endless. Why we have infinite? Because we have a continuous distribution of mass, and we can wiggle it how many times we do want. Now, do you really want to play the guitar? Look here. L is given by the string. So if you take a guitar with a given length, it's given. What about the frequencies? Now we have lambda, we have V, and you can discover now these are the frequencies that you can play with your string. And you know what? They are called harmonics. Why? Because, okay, now length is given. What about velocity? Well, it's decided by the tension and by the density. But once you fix it, it's given. The fundamental mode will have n equal 1. The second one will have n equal 2, 3, 4, forever. They are all multiples of the same fundamental frequency. And you can call them a set of harmonics. Do you want to listen to them? Well, we've already done that. Okay, we can close this. I'm a little bit scared today, but it cannot be the first time that you study in your career, but I'm sure that you have already studied it. But your faces, it seems like if we are doing string theory in 26 dimension. That's just one dimension. No, it should be. Where is it? No, that's okay. That's okay. Where is it? There it is. Let me first test it without sound. You know what to do. Sorry, guys. I'm a little scared. Why it's not? No sound. You have to use your imagination. Let's not give a sound. This is noise. By the way, let's try. Now look, this is a string. Okay, you can say no, it's not a string. It's an animation of a string. Look at this. That's the vibration of the first mode. This is the vibration of the second mode. This is the vibration of the third mode. Fourth, fifth, whatever. I could play infinite set of this. Now, during the tutorial, I guess, when I pluck the string, I will excite. It's working. If I plug it here, now look at the modes that I'm exciting. If I plug at the center, the fundamental will dominate. If I plug near the edge, higher harmonics will be present in the sound. That's called timbre of a sound. If I would be able to play just the fundamental, but maybe this is not coming. Okay, it's not working for single modes. That's the point. Okay. So I can play this, but not the single modes. Now what is funny is that we have considered a system with its dynamic equations, wave equation. We apply the boundary conditions, and the boundary conditions are deciding the eigenfunctions. And the k's are not free, they are quantized. If you quantize with numbers, you quantize the wavelengths. And the frequencies are quantized. You can call this eigenvalues. So we have a differential operator with boundary conditions, and we found the spectrum. It's a complete set. The modes of the string can be used to write whatever is happening on the string. Now, if you think about it, this is a mathematical approach. We have equation, we separated variables, we found the solutions, a set of solutions, it's a complete. We're using maths to describe physics. In the other case, what we have done is to use physics. We have a progressive wave, it's bouncing, it's interfering, and we found the same expression. Standing waves are physically generated by the interference of progressive waves. But from a mathematical point of view, we can use the modes of the system, standing waves, also to write progressive waves. It's a dual complementary word. What is important is that you remember that this n can go to infinity. But why? Because we have a continuous distribution of mass. But actually, sooner or later, we will have a distinction between atoms in the string. We cannot move the mass between them. Of course, those distances are so small with the typical wavelengths of acoustics, of seismology, that we are not able to look for the holes. We don't have to care about the holes between atoms. Okay? By the way, these are called harmonics. Why? Because these are multiples of a fundamental one. In terminology, you can use fundamental mode, first higher mode, second higher mode, or harmonic number 1, 2, 3, 4, 5, 6. What's next? What we have to do now is to play with other boundary conditions. Let's imagine that we are so good, so nice, we're like wizards, that we can create a string not with fixed ends, but with free ends. So we put here 2 sticks with 2 rings, and they can oscillate without any friction. It's a string of the same length, but with free ends. Tell me in 1 second, what should I change in the blackboard for these new boundary conditions? No rocket science, just thinking. Well, the boundary conditions now will not be these ones. They will be the force has to be 0 on the 2 sides. You could say, wow, everything has to be done again. But what is enough is to take these ones. because the differential equation is the same. And what you have to do now is to imagine a stick, a ring here, and a string inside. Oops, that's terrible. Now, the wave function, the eigenfunction, will be maxima at the sticks. Okay? So what we have to do is simply to consider cosine of k and of L equals 0. What should I change? Nothing actually. But not in pi, but pi over 2. That's the same. And this will be the same. But the eigenfunction will be a cosine, not a sine. Boundary conditions are deciding which functions to pick. Homework, the last unofficial one. It's already solved in the slides. What if I consider a string with a fixed and a free end? We are so strange musicians, but now we want to play this strange guitar. In principle, we can. What's going to change now?
The boundary condition.
Yes, because now displacement has to be 0, and here displacement has to be maximum. If you plot it, it has to be something like that. So it will be a sign for this boundary condition. But it has not to be 0 at L. It has to be maximum. So you're going to change this. And you have to be careful. Because it has to be over 2, but this cannot be an even number. And what's going to happen here will be this. And n has to be odd. It's simply a matter of playing with boundary conditions. Now you should say, come on, no string instrument is using free ends. All the string instruments that we can imagine are using fixed ends. So who cares about this? Right. But there are two important systems that are using free ends. And the first one is the one that we are going to study now, in just a minute. But it's nice because it's simple and you can play. Because when you play a clarinet or a flute, you're playing with free ends for an air column. Good. The other system, well, it's a little bit more complicated because it's the Earth. Because the Earth, on its surface, actually is having a free boundary condition, not fixed. It's not rigid. Okay? We can move it. An earthquake is moving it. But every time it's trying to go back at the equilibrium, causing the force to be 0, like a liquid, when you throw a stone in a pond. Okay? In that case, it's gravity, the restoring force. In the case of the Earth, it's the elastic force. But it's a free end. It's not rigid. Okay? That's why now it's time to play with another animation. That is giving birth to this one. I hope it is here somewhere. Oh. It's not here. Let's charge it. Okay. We're going to play with flutes. Whatever cultural musical tradition of a region, of any region of the world, maybe these are the most ancient instruments with different sizes, with different tricks to perturb during the column, but okay. You can play a flute. A flute technically has an open end and an open end. In many cases you are playing it on the top with some edges, but it's open. It has its lengths. It has air inside. Earth atmosphere, with a given temperature, with a given composition, but we cannot play. You know, on a string of a guitar, you can play with tension. You can play with density, changing the strings, right? Here we cannot. What we can play is with length. Oh, by the way, on the guitar, you can play with length using the keyboard in a discrete step or continuous step like in the violin. You're changing length. Now, what about this? Now, let's give a look to the molecules. Molecules now are are representing sound waves. And they are longitudinal. Please remember, typical waves in the string are transverse, these ones are longitudinal. What's going to happen here? Well, in terms of displacement, it's going to be maximum at the two edges. But pressure will be zero there. Also because when the air is getting out from the flute, what about pressure? Well, on the other side, there will be an entire world with infinite impedance in pressure. So it will be a zero for pressure, but maximum for displacement. That's why this is the plot of the envelopes of the modes in terms of displacement and pressure. Please do remember that for sound waves, we have many ways to represent it. Displacement, density, variations of density, variation of pressure. Okay? And displacement and variation of pressure are out of phase. Where one is zero, the other is maximum, and vice versa. That's why, for sound waves, with modes inside their columns, we have to remember what we are plotting. Displacement or pressure. That's why you see they are totally complementary. Now, that's the first mode, the fundamental mode of an air column with open ends. What's going to happen? And you cannot change the air because velocity, sound with velocity, is decided by the air and the temperature. You can play with lengths. That's why sometimes flutes have tonal holes. You're changing the length, the effective length. Okay? Now, what can I change here? Well, for example, we can look for higher modes. Now, the rule is that here we have always a maximum, and now we are adding a node in pressure or two nodes in displacement. And we can go higher. I don't know how much higher. You can wiggle the air how many times you want. So if you want a terminology, you can call it fundamental, first overtone, second overtone, as you can see here. Or first harmonic, second harmonic, third harmonic. What you have to do is just to bookkeep the number of nodes. You can increase them. And you see on the top the vibrations. Remember, these are longitudinal waves. Okay. Let's go back to the fundamental. What if now I close both sides? Uh-oh. Nothing is changing in these formulas here, but what we have to change is the eigenfunction. Because now displacement has to be zero on the two edges, and pressure will be maximum. So what we have to do is to reverse the plot. What I'm trying to tell you is that actually the modes in air columns and strings have the same pattern, but we have to remember the differences. longitudinal transverse. For strings, usually we use just displacement. It's easy to plot. For some waves in air columns, well, maybe pressure is better than displacement. So we have at least two representations that are complementary. And you see, I can go on. Let's go back. What can we do now? Well, we can play a clarinet and not a flute. A clarinet, any air column instrument with an edge here, also a trumpet. The edge is made by the lips, okay? But there has an anti-node of pressure. And you see here, displacement is 0, pressure is maximum. And now you can go on. But you have always to take care about boundary conditions. Boundary conditions are deciding which solutions to pick from the solutions available from the equations that are being separated. What about the wavelengths? Please remember, here it is not so evident. But maybe yes. Now look at this plot in terms of displacement. You can imagine that to complete the wavelength, you have to go for 4 times the length. With the flute, you need 2 times the length. Now the number of harmonics is still infinite in the 2 cases, but please do remember that for a closed open air column with the same length, the fundamental node will be lower, 1/2, because it's V over 4L. For a flute, it will be V over 2L. And you cannot put there even numbers, just the odd ones, 1, 3, 5, 7. In terms of perception of the 2 instruments, the clarinet timbre is a little bit poorer than the flute one. It has less harmonics, and they are not exactly spaced in the same way, because there is 4 instead of 2. But that's for music. So to sum up, in these systems here, what we can do is to start from a very simple picture like this and look at the geometry of vibration. I'm sure that you don't want to do separation of variables anytime, but what you can remember as an easy way to take home all the apparently messy algebra here are just a few things. The first thing is this, and that's valid since high school. Space is equal to velocity times time. Thank you. This is true for every wave system. You do agree with me?
Yes.
Good. Then you take your string. What you do, I'm really terrible in plotting lines here, but what you can do is, okay, you think about the length, and you think how to accommodate here modes. 1, 2, 3, 4, 5, 6, okay. Now looking at this plot here, you immediately get that lambda n has to be 2L over n. Immediately. Just geometry. And you have just the length. Then you do remember that expression there, and immediately you get this. And now you can play the guitar. If you want to be a sort of a crazy player, you can play with boundary conditions here. You put here a 4, and then it has to be odd. Or you can play a 3-3. Same expression, but the eigenfunctions will be cosines and not sines. So you have everything just plotting lines. But please do remember that these functions here arise anytime that you solve an equation by separation of variables. In the last lecture of the course, and I'm scared about that, we will try to do that for the Earth. Bad news. Sine and cosines will not be enough. And new other differential equations will arise, and the base for those equations will be harder functions that are not exactly periodic. Like Bessel functions, like Legendre functions. And those functions have a characteristic. Their zeros are not equally spaced. Sine and cosines are beautiful. That's why we can speak about harmonics. But for Bessel functions, for example, if you play a drum, you don't have harmonics. That's why it's very difficult to use drums to build melodies. In those cases, you don't speak about harmonics, but you speak about overtones. And you cannot say, oh, it's an integer number. So what we have done today, actually, was to do this. And to get this. Do you want to be sophisticated? Okay, separation of variables, boundary conditions, you get this. Once you have this, you get the frequencies. Okay? And once you get this, you can do beautiful interpretations. You can call them harmonics or overtones if they're not integers. What you can do is to obtain wavelengths, and that's the summary of what I was doing on the blackboard. You see, that's the boundary condition. The first is telling you, throw away cosines. They are not 0 in 0. Sorry for that. The other one is giving to you that one. And now you can play with boundary conditions. You can make your plots. And you can do also quantum mechanic interpretation if you think about orbitals. Well, we will do this not for quantum mechanics, but for seismic waves around the Earth. That's why we will speak about the Earth free modes. And what's next? Okay. Now, you can play with other boundary conditions. You can take a fixed and a free end. And making those plots, you see that you have always to accommodate this as a 0 and a maximum. What is changing? You have to put a number 4 here, and n has to be odd. And you can do the same with standing waves in air columns. Same. If you're lazy, you can take the same formula for air columns using the one for the string. But please do remember, please do, that D is different. Mersenn's law, if you want Laplace law. The two velocities are different. And in one case they are transverse, in the other case they are longitudinal. But you can bookkeep them in the same fashion. And to play, you can play with boundary conditions. Now, it's time to go back to this one. Now maybe you can appreciate it. Because what is the difference between this animation and the one that we have been admiring during the last lectures? There is an edge, there is a wall at the end. So particles cannot move there. It's a boundary condition. So we started, we don't have a string here. There is that one, but I cannot play with this. Okay? So we can imagine it, we started playing it when it was infinite. And we have been wiggling it, studying wave functions, going on forever. And on infinite string, you shake it, it's going. Now it can come back. And in the rigid version, you can use this. Now what? It's the opposite of a string. Well, it's a stiff system. But what about the two ends? Well, now I'm pinning it, but this is better. Now this is fixed. This is free. Vibrations, fundamental vibrations, will be decided by the stiffness and its length. So I'm not that good as a fixed one. And this is different. So the length will be different. Rigid and free. Many percussions are used on the vibrations of, for example, metals or other things. Wood, in many cases. They're not harmonic. That's why you use them for rhythm. But let's give a look to this one now. So now we have a source at one end that is giving a maximum displacement, and a wall at the end that is giving zero displacement. How to accommodate energy there? Well, now let's think about in terms of physics. A progressive wave is generated. It's bouncing and then interfering. According to its length, you can accommodate there some nodes. How many? Well, in this case here, you can count them. 1, 2, 3, 4, except the final, plus the final. Now let's give a look to the animation. The particles. What is the difference between this one and the one that we have been admiring during the last lectures? Well, now all the particles of the system are oscillating with the same frequency, right? Good. As before. But wait a second. Because some points will never oscillate. Never. They're always standing. Some points are oscillating at its maximum. Forever. In the previous case, when the wave was arriving, we were oscillating back and forth with different phases inside the system. It depends on where we are, where you're seated on. Now not. Space and time are separated. You can be a node, you can be an anti-node, you can be in another place. So these are the modes of the system. Frequency is the same, and actually it's dictated, in this case by here, but you have to look for interference. That's why it's not easy to play air columns. You have to look, you have to perturb them with a frequency that is near to their natural ones. You have to look for resonance. Otherwise you will squeeze a trumpet with terrible sounds that will not last. But the principle is the same. Please do remember that for some waves, they have a tricky nature, but you can plot them in terms of displacement and pressure. You see displacement and pressure. They are complementary. As you know, since you developed beautifully your homework during the weekend, displacement and pressure, cosine, sine, and vice versa. You can decide to play here the boundary conditions, open end, closed end, open, open. For the string, oh well, that's easier. Usually it's fixed. 1, 2, 3, 4, forever. So, what we did today was simply a recap of standing waves, or if you want to call them modes, of 1D systems. But we also concentrated on the terms of impedance, reflection, and transmission of energy. Then, and this will be the restart of the next lecture, because the next lecture will have two sides. A solid state one that will be giving to you the first official homework about phonons, don't worry. And the other one will be a sort of a tutorial using Fourier. Maybe we can use the last 10 minutes starting that one. because it's more classical. What is that? This one. Okay. What is this? Well, it's a picture. You cannot hear it. But actually, it's the visualization of a part of a speech. An example is what is boring you today from my larynx, from my lungs that are giving the source, from my vocal folds that are vibrating, my emission, propagation, your eardrums, also if you're sleeping, are vibrating with given frequencies. Then they're entering into their amplified, mapped, cochlea, perception, and sleeping. By the way, what you can see here is that a normal speech or a piece of music or some noise is not this. Do you remember? Now maybe it's working. Let's be boring. Maybe with this you can sleep. I would sleep. Okay. Now, this is this one. With omega at 220. Who is deciding K? Who is deciding A?
Initial condition.
Yes, but the player, that's me. Do you want to have a larger A? I hope. I'm changing A. Right? I'm going also in some non-linear cases. Okay, that's A. Who is deciding K? What? The source of the system? Velocity. Because inside K, we have frequency, and I can decide it, and velocity. In the sound wave case, today is hot. So it's fast. Temperature. Or if you want, the bulk modules. This vibration is partially coupled also in this table here. I don't think I have the proper tool here. Yes. Ah, I cannot show it. What is? Let's see if I can break everything. Okay, I never did this experiment. Is something I no HDMI.
It's
Oh. Okay. Now what I'm showing to you without any desire or advertisement here for any, but this is a free tool that is making what we can call a Fourier spectrum and a spectrogram that is nothing else than a Fourier spectrum running in time. This is what we're going to briefly discuss during the next lecture. Okay, what do you see here? You see, now my speech is transient here. Okay. What you notice here is that there is a quite evident line here. Now this part of the wave is a sound wave emitted by those speakers, making us sleep, okay, and heard by the microphone of my old mobile. And you see it's here. And I would like to ask you, what are these additional lines? But, okay.
This is the only sound wave because we do have another sound waves.
Oh, now you're speaking of that.
Another waves
Which ones?
from the medium.
You mean noise?
Yeah, noise or another turbulence may affect our sound wave.
Okay, but these are not those lines. That's noise. Noise actually is characterized by a set of frequencies, and no one is appearing, is standing there. Like speech. For example, if I say A, O, E, O, U, I'm changing that, you see here? These, especially vowels, are created by formants. Good. Now, that's the boring part. What about this? They seem repetitions of something. Really, I never did this experiment. My guess is these are some resonances of the room. So we are like in the Earth, but our Earth is a room, is a hot room today. And maybe moving the microphone around, but I cannot do it. Their amplitudes are going to change according to the position. Definitely here, you see, maybe some other lines that are there are related to the resonances of this box. But you see that now I'm changing the amplitude. Still is there. Amplitude modulation, you remember bits? Okay. This is one part of the experiment. And it's actually what we're going to discuss in 10 slides. Yes, on the next lecture. But maybe, and I never tried it, we can listen to the vibrations of the table. Now it's very tiny. That's not tiny. Okay? Now, this is not using the microphone. This is using the accelerometer that is inside. And so it's feeling the vibration of the table. Maybe part of this vibration is coupled there, but as you can see, it's not very evident. Maybe, we can go to the spectrum. It's not easy, also because the scale is ending. Maybe there is a peak at 220. That is the frequency that I'm playing. But usually in seismology we use just up to 20 Hertz. So maybe there is a coupling between the sound and some vibration here. But it's at frequencies that are too high for the system here. So you see that there is something periodic. Stop it, let's play it. What's happening here? Sensing, okay. Okay, you see that there is something here. You can call it noise. Definitely now it's noise because it's boring. It's noise if you want to wait for this. Okay? But actually it's sound. So it could be a source. Well, sorry for someone who's knocking. Or is it noise? It was you? Okay. Now, what I wanted to show here is that the typical tools for sound, but not only for sound, for every time sigma, maybe are related to the Fourier spectrum. What you have seen here, and I want to close, well, okay, I hope you do remember, maybe we're going to use it also in the next lecture, is that the vibrations of the air with a single note, they were sensed by the microphone and mapped from time domain to frequency domain. That's Fourier. And if you run Fourier spectrum in time, you have what we can call a spectrogram that is very used in acoustics. Similar features can be used for other transients, like seismic waves. But, okay, they deal with different frequencies. Remember, acoustics is from 20 Hz to 20 kHz, just for a typical human ear apparatus. Seismology usually is running from 20 Hz down until 54 minutes. But the principle is the same. So on the next lecture, we're going to discuss briefly about part of the theory, about Fourier, but we have already seen it. And then we will go back for the last time about discrete systems. And we will see how the string modes will appear in a lattice. That's it. Then we will start with elasticity theory. So going towards the table and the graph. I hope that the Moodle portal system is going to be back sooner or later. It's not in my power. I'm sorry about that. If a problem persists, I will try to distribute the PDF of the lectures just by email, but I hope it's going to be fixed. Okay.